Hello, in this tutorial we're going to be looking at the Bohr's model that indicates the energy levels in a hydrogen atom. And we'll discuss briefly how this model is a little bit outdated because currently we use quantum mechanical calculations to determine energy levels, especially in more complex systems where we have more than one electron present. We have computer programs that can help us with those calculations, which can become quite tedious if we go beyond anything more complicated than very simple atoms with one or two electrons present. However, the Bohr's model really does perform a fairly decent prediction of energy levels when we have a single electron atom. Now, usually if we're talking about a single electron atom, well, the only case on the periodic table where we would have that scenario would be when we have a hydrogen atom. Every other element on the periodic table would have more than one electron, and we find that the calculations involving the Bohr's model and the equation we'll be looking at today, which is the Rydberg equation, will not correctly predict those energy levels once we have more than one electron present because of more complex considerations of repulsions and quantum mechanics that are occurring there. However, if I do have a one electron ion, we can make corrections to that to determine with the Rydberg equations energy levels when there's only one electron present in those ions. For example, if we were to have a helium atom, which normally has two electrons, if it were to lose one electron and form the helium plus one charged cation, which we don't expect to happen readily because of the stability of helium, but if it were to occur, we could use these calculations with a correction factor, which is going to be Z here, when the charge on the nucleus is something other than just a 1 for hydrogen. So if I had helium, I would put a Z value in here for helium. If I had the helium plus 1 charged atom where I still only have one electron because I had lost the second one, well, then I could put in for my value for C, I could put in a 2 and square that for this top term here. However, most of what we'll be looking at today will be a scenario where we have hydrogen. And if we have hydrogen, we're going to go ahead for the Z term for the hydrogen atom. We're going to put a Z in as 1, so 1 squared is just 1. So the equation that we'll usually use to predict the energy levels in a hydrogen atom will involve a constant, which has been determined as the Rydberg constant. You do not need to memorize the Rydberg constant. I would give it to you on a test, but it's 2.18 times 10 to the negative 18th joules here. So we can take the negative of the Rydberg constant times 1 over n squared. Now the n value will be a quantized energy level. Now when they were studying the atoms on the periodic table and focusing on hydrogen's simpler scenario, they found that, surprisingly, the energy levels related to those electron transitions in a hydrogen atom were quantized. That means there were only certain energy level differences that were allowed as electrons went from lower energies to higher energies, or vice versa. It wasn't as if every single possible energy transition was occurring. There was only certain quantized or certain allowed amounts of energy changes that were occurring. And so if we ended up with these quantized energy levels, we could have an energy level in the single electron hydrogen atom where we had an n equal 1, where n is going to relate to my energy level for the Bohr model. Later on, we'll see that we continue using this letter n in quantum mechanics to represent the principal quantum number. These n values will always be whole numbers, so the lowest energy level for an electron in an atom would be in its ground state. So n equal 1 is the ground state. For the hydrogen atom. If we have an electron in a hydrogen atom where there's only one electron present that were to absorb energy from its surroundings in the form of electromagnetic radiation, we can only absorb energy differences that are quantized, that are certain allowable amounts that would go to n values of whole numbers here. We could have an n value of 2 for my second energy level, or n equal to 3. We can say that if we're dealing with n values that are greater than 1 in the Bohr's model, in those scenarios we have excited states. So the electron has been excited from its ground state into a higher energy level. Now we can't have an n value that's a fractional amount, so I couldn't have an n value of 1.2. Those energy levels are not allowed. As we'll see later, this is related to the allowable quantum mechanical wave functions that can occur in three-dimensional space, where we have a stable electron with respect to its energy levels around an atom's nucleus. However, for the Bohr model, they had observed these quantized energy levels, and Bohr suggested, well, perhaps these were like a mini solar system where we have the nucleus as the center of the solar system, and we have these orbits for the electrons. So he was talking about these electron orbits, these orbitals that were allowed, and when he considered that, he was viewing it in a fashion that is no longer current with the current models. The current models no longer consider these types of orbiting electrons. We don't really consider the electrons as particles like they originally did. With the Bohr model, we actually think of those electrons as electromagnetic we think about those electrons as having not only particle properties, but also wave properties. And so we end up with the quantum mechanical wave function, considering the stability of that the wave pattern with respect to an electron, and that stability allows these quantized energy levels, rather than having only certain types of orbits allowed, as the Bohr model has suggested. So realize the Bohr model is a little bit outdated, but we still look at it because it does help us predict energy levels fairly effectively. Okay, so when I want to calculate the energy levels for these different quantized energy levels in the Bohr model, we can calculate the energy level for n equal 1 for the ground state, or 2, 3, 4, 5 excited states as they become greater whole numbers, by taking the negative of the Rydberg constant times 1 over, if it's a hydrogen atom, my z value is a 1. If it was a single electron ion, we'd have a z value with respect to the number of protons in the nucleus becoming greater than 1, so helium would have a 2. If we had a lithium plus 2 charged cation, we'd have a z value of 2, but we don't run into those scenarios very often, so usually I'll put a z in as 1 when I'm just dealing with the hydrogen atom. Now my n value is going to be whatever quantum number, whichever energy level I'm looking at. So the ground state would be a 1, the excited state with an n value of 2, I'd put a 2 squared in the denominator here. That would allow me to calculate each of those energy levels for those electrons. Now, as we look at these quantized energy levels, we find that their spacing becomes closer and closer together with respect to larger n values. So the spacing gets smaller and smaller and smaller, but with respect to the difference in spacing. If we consider an electron, though, that were excited in a hydrogen atom to a higher energy excited state, and realize my excited states are going to be my n2 all the way up to my n6, the ground state would be my n equal to 1. If I have a transition, let's say I have a transition from n equal 5 to n equal 4, the spacing here is closer together. So if I were to ask you the difference in energy between the fifth and the fourth excited state, this is a smaller difference in energy because the spacing of the energy levels is closer. So as I release that energy, it's going to be a smaller amount. So we'd find that in that case, we would end up with that energy being released as a particle of electromagnetic radiation that we call a photon. So we would find that that transition would be a lower energy photon. So that would be my lower energy photon released. Now if I have a particle of electromagnetic radiation that's released from a larger difference in energy levels, so we have the n equal 3 excited state to the ground state of n equal 1, the difference in the energy levels here as we get to smaller n values for my orbital numbers or my principal quantum numbers, I'm going to find out that I have a much larger difference in those energy levels, and so I'd have a larger energy photon. So I'm going to have a higher energy photon release of electromagnetic radiation. So you can make some general predictions about the magnitude without even having to calculate them with respect to memorizing that the spacing between the n values for these quantized energy levels, these different allowed energy states, become closer and closer and closer together. Now, one thing you think about with quantized energy levels, if we were to relate that to a ladder, let's say instead of looking at these quantized energy levels in the Bohr model, let's consider gravitational energy levels when you're climbing a ladder. If we're climbing a ladder, we can think about having quantized energy levels with respect to the rungs on the ladder. We can only put our feet on those rungs. We can't really stop as we're climbing and have our foot stable and at an intermediate location where the rung of the ladder isn't at. It's a little bit like this, except we would have a very odd ladder with the spacing of the rungs getting closer and closer and closer together as we get to higher energy levels. So that's kind of what we're looking at here. We can't have a transition that's in between these. I can't have a transition of, let's say, 1.7 to 1. That would not be an allowed transition because I wouldn't have a stable electron with a quantum number of between 1 and 2. Those are the only allowed stable states. If you think about this, it's a little bit like imagining having the wave properties of these electrons. So we're starting to see that particles, small particles especially as electrons, start to exhibit wave properties that we can begin to observe. If you imagine a wave on a guitar string, for example, we can have standing waves on the guitar string, but I can't have a fraction of a standing wave on a guitar string. It's not allowed. That's kind of what we're seeing here. The wave properties for electrons will have destructive interference between the waves if we end up having a partial wave present in the quantum mechanical calculations of the wave function for the electron. So here we have to be very careful. We can't have these fractional amounts for n. Okay. So realize all of these are excited states. The n equal 1 value is the ground state. Memorize that the spacing of the energy levels becomes closer and closer and closer together as you get to higher energy levels. So if I were to look at a diagram for the hydrogen atoms with the Bohr model with the spacing of the electron orbitals, I can have my n equal 1 ground state, my excited state 2, 3, 4, 5, 6, 7, up to infinity. The spacing gets closer and closer and closer here. Now we can look at these transitions of electrons if we were to have an electron in an excited state transitioning either to a lower excited state or to the ground state. That energy difference will be the energy of a photon being emitted. Now, oftentimes when I talk about the energy of a photon with respect to an atom either absorbing or emitting a photon, we're going to use the absolute value of the energy difference here off of a table like this because I really can't have a negative energy for the photon. If I have a positive or negative sign in my calculations, that just tells me whether or not I'm gaining or losing energy with respect to the hydrogen atom itself. So that would tell me whether or not I'm either absorbing a photon of energy or releasing a photon of energy. So if I'm releasing energy, I'm going to get a negative value here. If I'm having a relaxation from excited state to a lower excited state or to the ground state, so I just take the absolute value of that energy change to calculate the energy of the photon. If I'm absorbing a photon, I'm going to have a positive value, and that would occur when an electron was transitioning from a lower n value to a higher n value. Now I'd find the energy levels that were differences that are not these whole numbers, I won't observe those photons being absorbed or emitted, so I wouldn't interact with those portions of the electromagnetic spectrum. So I end up getting what are called line spectra. I have specific allowed energy level differences that I'm looking at. Now, if I want to find out the energy level differences between two of these quantized energy levels, well, I can imagine that change in energy will be related to the energy of my final state for the electron minus the initial state. Okay, so if I, for example, were wanting to calculate the energy difference between an n value of 3 and an n value of 2, well, we could use our Rydberg equation to calculate the differences in these two energy levels, and that change in energy would, if I take the absolute value, will be related to the energy of the photon that would be emitted in this case. Okay, so I'm using the following equation. The energy of one of my states for the electron is going to be the negative of the Rydberg constant, which I would always give you on a test, so you don't need to memorize it. I take that times for the hydrogen atom, a z value of 1 squared, which is just 1, divided by my n value, whatever it is, squared. I could calculate the energy level for the initial state, so I'm just doing this calculation twice to find these two terms so I can find the change in energy. The initial state will be equal to the negative of the Rydberg constant times 1 over the n value for the quantized energy level here squared for that initial state. And if I take the difference between the answers of those two cases, I can calculate this change in energy. Now, if I want to combine these two equations for my energy change for the final state, I can plug that equation in here. And for the initial state, I could plug my equation in here. And so we're going to generate a new form for the Rydberg equation where I can just plug in the Rydberg constant and my initial and final energy levels. Now, you notice there's a change in sign in the Rydberg constant. The reason for that is as I combine these two terms, I went ahead and changed the sign on the two terms, so I ended up with my initial minus my final. As I did that, I basically multiplied through by a -1 with respect to my terms, and so I end up with having a positive Rydberg constant. So be careful that when you're using this form of the equation, we're putting in the positive form of the Rydberg constant rather than the negative form, so be cautious about that. Now, my Rydberg constant I would give you on a test. The value, though, is 2.18 times 10 to the negative 18th joules. You might want to write that down for reference so that we can use it in some of our calculations that are coming up. Now, let's imagine if we're looking at the Bohr model of the atom, even though we don't consider electrons actually being present in orbiting spaces around the atom, we really think about the quantum mechanical theory these days with respect to having a wave function. Bohr originally had imagined, well, what if the electron was orbiting the atom, and if we have the energy, let's say, of the n value of 4 for the electron, and the electron was relaxing to a lower energy excited state, let's say to n equal 1, well, in that case, we can see that the transitions in the energy levels could be calculated using the Rydberg equation. We'd find that if I were then to take that energy and relate it to my wavelength, and so that would be equal to the following equation. My energy that I calculated for the photon, I can take the Planck's constant times the speed of light divided by wavelength that we had looked at in our previous tutorial on this chapter. If I solve for wavelength, I can find that the wavelength is 97 nanometers, and so that's going from an excited state of 4 to a ground state of 1. As we end up going from let's say an excited state of 3 to 1, we get a wavelength of 102 nanometers. So we end up with having a longer wavelength, a smaller energy change. If I go from n equal 2 to n equal 1, well, in that situation, we're going to have a wavelength of 122 nanometers going from that excited state to that ground state. So we're seeing as we have a smaller transition between the energy levels, we're getting longer and longer wavelengths. Now, usually what I'll do is write this out with respect to the energy levels on the diagrams we've been looking at before, and as I calculate these energy differences from the Rydberg equation, I can just go ahead and calculate my wavelengths from each of the following equations. Okay, so I did the Rydberg equation that we were looking at in the previous slide, find the change in energy, the absolute value, plugged it in this equation, and I solve for each of my wavelengths, wavelength 3, wavelength 2, or wavelength 1. So I'm finding as I look at a larger difference in energy between my transitions, I should get a smaller wavelength. So this 97 nanometers would be equivalent to the transition of the electron from this excited state to that ground state. As we end up having that transition, we must have that energy emitted from the atom. That's going to be from that specific wavelength. Now, these are the only wavelengths we expect to be released during this emission process for these types of transitions. The only other transitions I might see potentially would be from other quantized allowed energy transitions like n equal 5 to 1 or 6 to 1, or intermediate excited state transitions like 6 to 5 or 6 to 4 or 6 to 3, or I could have a 4 to 3 or a 4 to 2. Those would be all the energy levels that would be allowed. Now, I only have certain energy levels that are allowed in the visible range of light, and so if I wanted to look at the emission spectrum in the visible range, well, I can find that for the hydrogen atom emission, we'll have certain allowed wavelengths from the emission processes, so we get certain quantized energy level transitions that allow us to see visible electromagnetic radiation released. Or if I talk about an energy for an electron in a lower excited state, absorbing energy from, let's say, white light, only certain wavelengths would be allowed with respect to these quantized energy levels. So let's say we start in an excited state of n equal to 2. So I have an electron in an excited state of n equal to 2. Let's say we have a photon of electromagnetic radiation coming in and being absorbed. Let's say we're getting a photon of electromagnetic radiation that's in the visible range. That's a kind of a blue-green color, a cyan color, if it's being absorbed by my hydrogen atom, well, that's the perfect energy level to go from an n equal to 2 to 4 transition. And I'd find that if I was absorbing electromagnetic radiation in the visible range, I would end up with a band that would be missing from the white light that was passing through my sample of hydrogen, let's say in the gas phase. I would be missing a band at 486 nanometers because it was being absorbed in order to cause a transition from n equal 2 to n equal 4 for my energy level transitions. However, if I were to look at, let's say, an already excited hydrogen atom with the electron at the n equal 4 excited state, and if that electron were to transition to a lower energy excited state, let's say to the n equal 2, now since I'm have that same type of energy transition, the same amount of transition in energy but going the other direction, I release a photon of electromagnetic radiation. Now the difference between either absorbing a photon of that energy difference or emitting a photon of that energy difference is whether or not we're going to be looking at an absorption spectrum or an emission spectrum. So if I have electrons exciting to lower energy levels, I would be emitting these wavelengths. So the n equal 4 to n equal 2 excited state would release cyan light with a wavelength of 486 nanometers. If I'm exciting an electron from an n equal 2 to n equal 4 excited state, I'm going to absorb cyan light at 486 nanometers. The wavelengths are identical because the difference in these two energy levels, whether I'm absorbing light or emitting light, is the same difference. So we're going to see those wavelengths at exactly the same position. Okay, now if we start to look at the different types of transitions that can be occurring, let's say we were looking at an n equal 5 excited state, which I don't have on this diagram, going to n equal 2. There's a larger difference in the energy levels, so I get a shorter wavelength. I'd get out here at 434 nanometers, a blue band. If I had a smaller difference in energy levels, let's say I had an electron in the n equal 3 excited state transitioning to the n equal 2 excited state. There's a smaller difference in energy levels. Those are a closer spacing between those two energy levels. So I'd end up with a longer wavelength being lower energy. So I'd end up with a band of red light at 3 to 2 nanometers for the transition. So just realize the emission spectrums always have a higher n value and the electron ends up in a lower excited state or the ground state with a smaller n value if I have an emission of electromagnetic radiation, if I have a photon being released. If I'm absorbing photons, I always start with an initial n value that's smaller and I end up with an n value that is greater when I have an absorption of electromagnetic radiation. So the final n value will be greater during absorption processes. It will be smaller during emission processes. So it's important to remember that and kind of have a little model of the Bohr's energy levels in your mind when you're thinking about this. Now, if we're just looking at spacing in these energy levels, we can also consider different portions of the electromagnetic spectrum related to some of these common types of transitions for the hydrogen atom. If I'm dealing with the hydrogen atom electron transitions from excited states to the n equal 2 energy level, this is called the Balmer series, and we can expect that the photons released for most of those transitions are going to be in the visible range with the spacing of the energy levels. If we go from excited states all the way to the ground state for Bohr model emission processes, we find that those energy levels are greater than the visible range of electromagnetic radiation, so we're going to be out in the UV, right? Because the UV electromagnetic spectrum is going to be higher in energy, shorter in wavelength than the visible range. So we expect that we're going to have wavelengths for the UV that are going to be less than 400 nanometers. Now, if we start to go into the Paschen or the bracket series, we start to get smaller transitions in the energy levels. There's a smaller spacing between those energy levels, so we end up with having less energy. So we're going to get wavelengths for these regions that are going to be longer, smaller in energy. They're going to be longer than 700 nanometers as we start to go up in these ranges. So that's kind of good to have that map in mind. Okay, so let's consider a few calculations where we're using the Rydberg equation here to calculate the energy level for my transitions and the wavelengths involved with these transitions. Okay, so let's perform the following calculation. The wavelength in nanometers of a photon that's emitted by a hydrogen atom when its electron drops from the n equal 5 excited state. So that's going to be my initial value, right, for the initial n value in the Rydberg equation. And as the electron is going to a lower energy state, n equal 3, we're going to put my final value of a 3 here. Okay. So if I plug that in for my Rydberg equation, I go ahead and plug in my Rydberg constant. We put the final value of a 3, the initial value of a 5. So I go ahead and plug everything in as I've shown here. If we calculate the energy difference, we're going to get a negative 1.55 times 10 to the negative 19 joules. So I want you to think, what does this negative sign tell us? Okay. The negative sign for this energy level change means the electron ended up at a lower energy at the end of the process for this relaxation of the electron to a lower energy level. We can say in that case we have that energy released from the atom in the form of electromagnetic radiation. So we have a particle of electromagnetic radiation released in the form of a photon emitted by the atom. Okay, now if I start looking at energies of photons, I'm just going to use the absolute value of these energies. The negative sign just tells me whether I'm emitting a photon, and in this case, if I were to calculate a positive value, I would end up with, in that case, rather than an emission process, I would have an absorption process, and the electron would end up at a higher energy level. But I can only emit or absorb photons of electromagnetic radiation with respect to the quantized energy level differences. That's why when we were looking at absorption spectra or emission spectra, we were seeing only certain bands of electromagnetic radiation being either emitted or absorbed, because there's only these certain quantized energy level differences that are allowed. Okay, so if I want to calculate the wavelength for this transition, realize that we're using the equation that we've written before. The energy of my photons of electromagnetic radiation will be equal to Planck's constant times the speed of light divided by wavelength. And you should either have this equation memorized or be able to produce it from the equations we've looked at previously in the chapter. All I did was solve for wavelength. So my wavelength, if I multiply both sides by wavelength and divide both sides by energy to isolate that algebraic variable, we find that wavelength is equal to Planck's constant times the speed of light divided by the energy of the photon that's being emitted. Now, as I said, I'm using the absolute value here for the energy, so I put a positive 1.55 times 10 to the negative 19 joules, because it wouldn't make any sense to get a wavelength that was a negative length. I'm going to have a positive length for the wavelength. So I took Planck's constant in, which I would give you on a test, is 6.63 times 10 to the negative 34 joules times seconds. I've asked you to memorize the speed of light as being 3 times 10 to the 8th meters per second. I divide by the energy of the photon being released. I get a wavelength of 1.28 times 10 to the negative 6 meters. That's because my joules will cancel in this equation. My seconds will cancel, and I get units of meters. Now, if I want to convert to nanometers, I recognize that there's going to be 1 times 10 to the 9th nanometers for every 1 meter, or there's going to be 1 billionth of a meter for every nanometer. So if I go ahead and do my conversion, I find that I have 1,280 nanometers. Okay, so you might want to write down the Rydberg equation, because I will give you that on a test, and we're going to use that here in just a moment. Write down the Rydberg constant, write down Planck's constant, and let's try having you perform some of these calculations next. Now, if we're considering what we just observed here, from the n value of 5 to 3, we get a wavelength of 1,280 nanometers. That 1,280 nanometers, we'll notice, is greater than the visible spectrum wavelength. So we're going to be out here at longer wavelength. That's going to be out in the IR, right? If I had transitions that were giving me wavelengths that were below 400, we get out in the UV range. It would be higher energy. Okay, so for the last problem, we were having a transition in the IR range that we were looking at. So it's outside this visible range that we've been observing. Now let's have you perform this calculation. So I'm going to have your local instructors go ahead and pause the video and have you perform this calculation. I want you to determine what the wavelength is in nanometers when a photon is emitted during a relaxation process when the hydrogen atom's electron drops from an n equal 4 to the n equal 2 value. So go ahead and pause the video, have your local instructor help you if you're having trouble with this calculation. I've given you some of the constants and the Rydberg equation to help you with the calculation. Okay, so at this point you should have tried to perform this calculation using the Rydberg equation. If we're plugging in our values, we go ahead and plug in the Rydberg constant for my RH value. My initial state was where the electron began. So the electron began at the n equal 4 value. So I'm putting in 4 for n sub I. My final value for the electrons, n value, is going to be a 2. if I performed that calculation correctly, I should have ended up with a wavelength of 487 nanometers. That was the energy of the photon being emitted. Should have been a negative value because the hydrogen atom was losing energy. I took the absolute value of that to perform my calculation. I would end up with my value in meters, which I converted to nanometers to be the 487 nanometers. If you need help with that, please contact me or ask the local instructor for a little help with that calculation. Let's perform a similar calculation. Let's say that we're actually absorbing electromagnetic radiation. Let's say we're absorbing electromagnetic radiation and we have an electron that's in an excited state of n equal 2, and as it absorbs electromagnetic radiation from a photon, a single photon of light, being absorbed, it transitions from an n equal 2 to an n equal 4 value. As it performs that transition from 2 to 4, we end up with wanting to calculate the wavelength of the photon being absorbed. So go ahead and pause the video, perform your calculation here, and have the local instructor give you help if you need some. Okay, so at this point you should have performed this calculation and determined what the energy level was for this transition. And if we put the n value of a 2 for my initial state here, I use my Rydberg equation here, my Rydberg equation constant. My final state was a 4. So you notice it's kind of reversed to the last case. What we had was, in the previous case, we had the initial value of a 4 and the final value of a 2. Now what you should have seen is the only difference in your calculation is you should have had the opposite sign for the energy. And so what we're seeing here is we had a photon of electromagnetic radiation being absorbed. So we have a positive energy change rather than a negative energy change. If I calculate the wavelength using my equation that energy of the photon is equal to Planck's constant speed of light divided by wavelength, if I calculate that wavelength in meters and convert to nanometers, we find it's the exact same wavelength of 487 nanometers. So that's what we're seeing with the absorption and the emission spectra. We're seeing the exact same wavelengths when we're talking about either the electron transitioning in an excitation process, or when we have the electron going to a relaxation process to a lower energy level. We're seeing those transitions because of the quantized energy levels as being the exact same wavelengths. We're just talking about whether or not the photon is being emitted or absorbed in that process. So you should have had the exact same wavelength, but in this case the photon was being absorbed rather than emitted. That was the only difference here. Okay. So it's 487 nanometers. Now let's consider another scenario. What if we were to completely remove an electron from the hydrogen atom? Okay, so here's a situation. Let's assume that we have an electron and a hydrogen atom in the ground state, so an n equal 1 value. We're going to go ahead and completely remove the electron from that atom, and my n value for the final state is basically going to be infinity because I completely removed that electron beyond all of the excited state we've been looking at. So my n value here for the final, I'm going to plug in infinity. My n value for the initial, I'm going to plug in 1. So what we're finding is as we take 1 divided by a larger and larger value as we approach infinity, this term simplifies. 1 divided by this extremely huge number would simplify to basically a 0. So we would simplify that term. So this term would go away. So if we go ahead then and look at this equation, we would find that it simplifies to the following form. And if you were to plug in your values, we would find that you should have determined a value of 91 nanometers for your wavelength. Okay, so that's what we're looking at for the wavelength here. Now, with this in mind, sometimes instead of using the Rydberg equation to actually calculate energy levels, we might want to make some general predictions. So I'm going to go ahead and we're going to do a few multiple choice questions. I'm going to have your local instructors pause the video and have each of you try to answer the question, and then we'll go ahead and discuss the reasoning behind your answers. Okay, so the first question we're going to look at is which one of the following transitions for the hydrogen Bohr model would involve the longest wavelength of photon being emitted by the hydrogen atom. So we have the following choices. The initial n value of 2 to the final n value of 4, or a initial 4 to final of 2, or an initial 3 to final of 5, or an initial 5 to a value of 3. Decide which one of those would be the longest wavelength of photon being emitted by the hydrogen atom. Okay, so at this point you should have finishes the class trying to answer this one. If we consider the energy level differences, remember as we go to higher n values, the energy levels are becoming more closely spaced. So you should have kind of the following picture in your mind, and you might want to draw this out on an exam if you need some help. We're looking at these following transitions. Now we are looking for an emission process. Since we're looking at a photon being emitted, we're starting at a higher n value. So the only scenarios where we have emission would be the situation where we have B from 4 to 2 during the emission process, or D where we have N5 to N equal 3. If we consider the N value increasing from 2 to 4 or 3 to 5, those would be absorption processes. So the answers cannot be A or C here. If we're looking at 4 to 2, well, that's going to be this transition. If we're looking at a 5 to 3 transition, now the n values in both those scenarios are just changing by a value of 2. But the spacing is becoming closer as I get larger n values. So we're seeing that there's a larger spacing between the excited state of 4 to the excited state of 2, and a smaller spacing between the excited state of 5 and the excited state of 3. So if we're looking at the longest photon, is that higher or lower energy? The longest wavelength photon would be smaller in energy, right? The shorter the wavelength, the higher the energy. They're inversely related. So the longest wavelength photon would be the smaller energy transition here. That would be my 5 to 3 transition. That's the correct answer. Okay, so with that in mind, let's try another question. If we're considering the longest wavelength photon that's being absorbed by the hydrogen atom, okay, go ahead and pause the video and try this one. Okay, so if we're looking at absorption processes, well, absorption process, we're going to have an n value that is smaller and becomes greater. So the only ones that meet that requirement would be A and C here. We would have emission processes for B and D, so I can eliminate those from my choices right now. If I look at those types of transitions, 2 to 4 or 3 to 5, we can go ahead and look at these two types of absorption processes, 3 to 5 or 2 to 4. There's larger spacing with the smaller n values because the spacing starts to become smaller and smaller as we go to larger n values for our Bohr model of the atom. And as we're looking at these types of transitions, we can see if we have a longer wavelength, that's going to be a smaller energy change. So that should have been in this case, the 3 to 5 transition would have been the correct answer because we're looking at the smaller energy change with the longer wavelength. Okay, so what if I asked you the following question? Which is the shortest wavelength photon being emitted by the hydrogen atom? So the shortest wavelength photon being emitted. Okay, so if it's the shortest wavelength, it should be the higher energy change. If it's an emission process, we should be having a transition from an excited state to a lower energy state. So I should have a higher n value to begin with, going to a lower n value. So B and D are possible answers. And transition from 2 to 4 or 3 to 5, those would be absorption processes rather than emission processes. So those can't be my possibilities. If it's shorter wavelength, it should be a higher energy difference. So if I'm looking at my transitions, a 2 to 4 transition is a larger energy difference than a 3 to 5 transition. So with that larger energy difference, we end up with a shorter wavelength of photons. So we would say here, the best choice would be B. Now, if I want to know which of the following transitions would be the shortest wavelength photon being absorbed, go ahead and pause the video and try this one. So if I'm talking about an absorption process, I should have a larger n value for the final state. So my possible choices are either A or C here. B and D would not be possible answers because those would be emission processes. Okay, if I'm looking at the shortest wavelength, that should be the largest energy difference because the inverse relationship here. Remember, I can remember there's an inverse relationship because my energy levels are going to be equal to Planck's constant times my speed of light divided by wavelength. So there's an inverse relationship there. So the shorter my wavelength, the higher the energy. So if I'm looking at these types of transitions, again, I'm looking at the 2 to 4 and the 3 to 5 transitions. So it's the larger difference in energy levels that will have the shortest wavelength absorbed here. So we're considering the 2 to 4 for the absorption process, so A would be the best answer. So hopefully you're getting more of these correct as we keep practicing. Let's consider this scenario, which is the largest energy photon being absorbed by the hydrogen atom. Okay, so if we have an absorption process, then our only possible choices are A or C here. As we have the absorption of a photon, we're going to higher energy excited states. And if we're talking about the largest energy transition, we're looking at the larger spacing. Now that's going to be the 2 to 4. Well, actually, just a second. We changed some of our numbers here, right? So we have the 2 to 4 transition, or we have a 1 to 3 transition. And if we look at the spacing here from the n equal 1 ground state to one of the excited states, there's a much larger spacing. So the actual answer here would be the 1 to 3 would be the largest energy photon, so it would be A. We have a smaller energy photon being absorbed from the 2 to 4 transition because we have a smaller spacing between the energy levels for that transition. Now, if we want to look at the smallest energy photon being absorbed, well, again, it's an absorption process, so I either have A or C here. B and D would be emission processes because my n value is smaller in the end. So if I consider that type of scenario with the 1 to 3 transition with the absorption process, I'm going from the ground state to the n equal 3 excited state, or I'm going from the n equal 2 excited state to the n equal 4 excited state. If we're looking for the smallest energy photon being absorbed, it's the smaller spacing between the energy levels. So that would be the 2 to 4 out here in the UV range of the Lyman series. So that 2 to 4 would be the smaller energy difference. Now let's consider the largest energy photon being emitted. So if we're looking at an emission process, we must be going from a higher energy level to a lower energy level. So it's either going to be B or D. I cannot have my absorption processes, which would be answer A or C, so I can omit those as possible answers here. If I look at the spacing, if I'm going from an excited state of 3 to the ground state of 1, or an excited state of 4 to an excited state of 2. And if I look at the spacing here, I want the largest energy photon being emitted, so that'd be the larger spacing, so that's the 3 to 1 transition. If I'm looking at the lowest energy photon being emitted, so emission processes are going to be, again, from a larger n value to a smaller n value. My absorption processes would be from smaller to larger. Okay, if I'm looking at the lowest energy photon being emitted, well, that would be the smallest energy difference between the energy levels. So that's going to be the higher n values of 4 to 2 will have a smaller transition than 3 to 1. So the lowest energy photon being emitted would be the 4 to 2 transition, so answer D would be the correct answer. Okay, so keep practicing that and try to build a model in your head about the spacing of the energy levels for the Bohr model and be able to predict what's going on with photons being absorbed or emitted with energy changes and how large those energy changes would be. Make sure you can predict what's going on with wavelengths, whether or not you have large or small wavelengths with these transitions, and then also relate to frequencies. Now, looking at frequency predictions is very simple because it's directly proportional to the energy of the photon. So if I can predict whether I have higher or low energy photons being emitted or released, well, I remember my energy of my photon is just merely Planck's constant times its frequency. I use a Greek letter nu for the frequency here, so they're directly proportional. So if I can predict the highest energy photon being absorbed or emitted, I have the largest frequency photon being absorbed or emitted. If I have a smaller energy photon being absorbed or emitted, I have a smaller frequency. So frequencies are a little more straightforward, but if you can predict wavelengths, you're probably in good shape. Okay, so go ahead and practice those today. Next, we'll be looking at using quantum numbers for making predictions. Okay, have a great day, everybody.